Hello and welcome to ENGPHYS 2P04 test number 11 prep. Today we're going to be looking at beam resonance, and specifically we're going to be looking at the 2016 final exam, question number 3. This is a topic that previously wasn't covered on the weekly tests. Instead, we would have had a major take-home midterm at this point on multimorph actuators. So rather than that, we have another test. Rather than just this topic appearing only on the final exam, it's now on a test as well. So this year there's going to be nothing on the exam that hasn't been covered in the tests along the way. Okay, so resonator beam analytics. The first question is, explain how we go from the full dynamic beam equation to the reduced beam equation and the relationship between V and V hat. So how this how the V that's solved for in here is related to this V hat at X. So first of all, how you get the dynamic beam equation in the first place, you might be wondering, where does that come from? Well, at the start of the beam resonance topic, we have this small element which is dx wide, and the idea is we look at the differential force on this element, and there's a V up on the left and a V at x plus dx on the right. So by using a linearization on V, saying that V at x plus dx is just V at x plus del V by del x dx, then you can cancel out the V at x and turn this expression into that one. And then by substituting in that V itself is the derivative of the bending moment, and the bending moment is EI times the second derivative of the vertical displacement per step in X, assuming that the displacement is only in the vertical direction, which means the beam stays mostly horizontal. So the displacements are small, basically. We don't have this curvature bending it into big arcs. Otherwise, this should really be the perpendicular direction to the beam's axis. So if the beam is on a 45-degree angle, then it would be up and to the left at a 45. So I guess that's 135 degrees from the horizontal. Anyway, it's always perpendicular to the beam's axis, perpendicular to whatever the longitudinal direction is on the beam. And as long as the moment is responsible for all of the displacement, then we can call this just the entire displacement, rather than saying that this is the displacement due to bending moment only. And again, as long as it's mostly small displacement, you can say that that is just in the y direction if we have a beam that is long in the x direction. Okay, so you substitute in this EI del squared V by del x squared for the bending moment into the definition or the result from much earlier in the course, that the internal shear force is the derivative of the bending moment per step in X. And then you substitute that in for the net force equation that we just figured out. To figure out the net force is negative EI del to the 4 V by del x to the 4 times dx. Then if that net force is from Newton's second law, mass times acceleration per unit step in x, then we've got that the acceleration in the vertical direction is this df by dm. So a little bit of force is equal to acceleration times a little bit of mass, and the mass per step in x being mu, the mass per unit length, and df by dx being this thing, leads you to the dynamic beam equation. Okay, so that's just a recap on where this equation comes from in the first place. Now to figure out this thing, what you do is substitute, right? So this is also covered in the lecture notes under the general solution part of it. So previously, in a general form of a partial differential equation like the dynamic beam equation, you would normally assume a general separable solution, then substitute in, separate into ordinary differential equations in x and t. And then use the boundary conditions, initial conditions, and linearity to solve it. But for this particular equation, we can instead just substitute in this assumed form, which is a harmonic solution. So we assume that it's cos of omega t plus phi for the time dependence, and then arbitrary spatial dependence v hat at x for the mode shape. So by substituting that in, you take two derivatives with respect to t of this, and you get negative the same thing times omega squared, and that's this. And then if you take four derivatives with respect to space, then that doesn't affect the time part, it just affects this, and you get a v quadruple prime at x. All right, so there you go, and that's how you, after canceling the cosine, get to the reduced form that is an equation for just the bending mode shape. So in other words, to close it out, you substitute a harmonic solution. So you assume that V is equal to V hat times cos of omega t plus phi. And then by substituting that into here, this equation turns into this after you take the derivatives with respect to time and space and then cancel the cosines. Okay, part B. When solving a cantilever, that is fixed free beam, this is the information, this is not the question. Using the dynamic beam equation, we arrive at a mode shape expression this, where beta n is the nth root of the generating function and omega n is beta n squared times the root of ei over mu. Okay, so instead for a beam which is pin supported at its left end and roller supported at the right end, write the boundary conditions, determine the mode shape, determine the generating function, and determine the first three resonant frequencies. So it says in determining the mode shape that you don't need to, so mode shape expression actually, you don't need to solve for C1, C2, etc. in order. Be careful not to divide by 0. All right, so part of these two things are actually going to happen at the same time. And then determine the first three resonant frequencies, plot the first three mode shapes on the same plot using Maple. Okay, so yeah. Information. If we go into the end of the general solution expression, then we've got this, this key thing. So from this, what you do is you substitute in e to the rx as an assumed form of the solution, and then you find out that r has to be one of these things. So fourth root of omega squared mu over ei, which we're just going to call beta. So it's either beta, I beta, and negative I beta, which by taking linear combinations of those things, you can turn into V at x. We'll go to a smaller. Hope you didn't get terrified by the massive equation there. We'll go to this thing by taking these linear combinations. So this is maybe we could insert another line there. So we could say v hat at x is equal to some, so we found like 4 solutions basically. 4 solutions, which are let's see. We've got e to the beta x, e to the negative beta x, e to the, go a little bit bigger than that, I beta x, and e to the negative I beta x. And then we can rewrite, which we can take linear combinations of. So maybe I'll split this up into different different parts. Yeah, okay. So essentially, when you substitute in this assumed form, you find 4 solutions, and you can rewrite them like this, where beta is equal to that, and then we're going to find a way to rewrite these solutions into this form. So you might be wondering, okay, where does that come from? It's just by taking linear combinations. So if you say, we can rewrite this using trig and hypertrig by taking linear combinations and using the identities. So cosh of x is equal to e to the x plus e to the negative x over 2. Sinh of x is equal to e to the x minus e to the negative x over 2. Cos of x is equal to e to the ix plus e to the negative ix, whoops, said it right, wrote it wrong, e to the ix plus e to the negative ix over 2, and sine of x is equal to e to the ix minus e to the negative ix over 2i. So you can verify These first two are kind of the definitions of cosh and sinh, and these ones you could think of as the definitions of cos and sine, but more likely you're going to be thinking of these as results of using Euler's identity that you can prove by substituting in for into these equations. Okay, into these definitions. So verify those if you're not familiar with them. Anyway, by taking those linear combinations of these previous solutions using beta x instead of just x here, we can rewrite this as the result there. Okay. So in other words, what we've got is that let's see, how do we want to do this? Solutions are that form where, and we'll get beta here, where beta is equal to this, and then we're going to be getting the boundary conditions. So how do we find the boundary conditions based on these supports? The solution works for any sort of boundary condition setup. So you didn't have to apply any boundary conditions to this equation in order to come up with this as the general solution. The boundary conditions come next. So where do those boundary conditions come from? They're actually a little bit earlier up in the notes. I think actually we talked about it in the flexure part. Let's find out where that was. Small deformations. There. Okay, perfect. So it's in the small deformations part of the flexure part of the note, of the notes, and there's this discussion of how different boundaries mean different things for all of the different conditions. So what this means is that a free boundary has guaranteed no shear force and no bending moment because there's no forces applied on it, but that means that you don't know what the angle or the displacement is. Whereas a clamped one, you know that it has no angle, no bending angle, because it's completely fixed. So this is the same thing as clamped, and no displacement. Again, same thing. So in the question, they tell you that we have a pivot joint at one end, which means the moment is 0 and the displacement is 0, but the angle and the shear force could be anything. And we have a vertical slider at the other end, which means the opposite. So it means the shear force is 0. There's no shear force applied, but that means we don't know what the displacement is. And the angle is fixed to 0, but we don't know what the moment is. We're going to apply whatever moment is necessary to make that happen. Okay, so pin supported at the left end. Let's let the left end be x equals 0, and the right end be x equals L as usual. Then the pin support at the left end tells us that V, so it can't move it at 0. So that means V hat at 0 equals, it can't have an angle. So that means that V prime is unknown. But because we can't apply any moments, that means V double prime is unknown, is rather 0, is fixed to 0. There's no moment applied at the left end, and there's no displacement at the left end. And so maybe we'll put this as, how to write this? Maybe like that. Pin support at left end. Then we'll say, just to give you a full view of that, we'll say here at the right end that it's roller supported. So what does roller supported mean? That's like a vertical slider, yeah? So being a vertical slider at the right end means it can go up and down. So the displacement is unknown, but the angle is fixed to 0, and so is the shear force. We're not resisting it with any shear force. So what that tells you is that V prime, that's the angle, is the angle at the right end, I should say, is 0, and V triple prime at the right end is also 0. So So that's slider / ruler, etc. at the right end. Okay. So there we have it. There's the boundary conditions. So to figure out the mode shape expression, we could do this analytically, but let's use Maple since we have it available. So we'll define V, C1 cos beta x plus C2 sine beta x plus C3 cosh beta x plus C4 sinh of beta x. Okay, so there's the V so far that we've got. And what we're going to be doing is setting derivatives of this are equal to 0. So maybe we'll go ahead and define that. Diff of V with respect to x. And there's our derivative. Let's go ahead and continue with that. V double prime is diff of V prime with respect to x. V triple prime is equal to the diff of V double prime with respect to x. Let's have a look at that one, see how it's doing. Okay, so no big deal. It's just inserting negatives and positives accordingly. So 3 derivatives of a cosine of beta x is going to be a beta cubed times a positive sine of beta x times c1. So if we have, so let's check. Differentiate once, we get negative sine. Then we go to negative cos. Differentiate again, we go back to positive sine. Okay. So checks out, at least for that one. Presumably the rest of this is looking good too. I don't see any big mistakes just glancing it over. Okay, so there's our derivatives of this thing. And now we can go and apply some boundary conditions. So we've got equation 1 would be that at x is 0, we have that the whole thing is equal to 0. So we know that this thing is equal to 0. We can simplify that and maybe get it to evaluate what those cos and sine things at 0 are. So equation 1 is just c1 plus c3. Let's go to the next line. Equation 2 would be substituting x is 0 into v double prime. And so we've got c1 minus c3. Now we don't care about beta. We don't want to try and solve anything for beta just yet. So let's divide by beta squared. And now we've got c1 and c3, both defined in terms of this equation. And maybe you can see what c1 and c3 would have to be for this. If you add these two equations together, then you have that 2c3 is equal to 0. Because these, remember, these equations, these are really just the left-hand side. The right-hand side is that we're supposed to equal 0 on these. And then with c3 is 0, the first one says c1 equals 0. Okay, so they're both 0. But we could solve that. Solve equation 1, equation 2. Now, when you can go and solve equations and what you can solve them for depends on how they're working out for the particular problem. So sometimes we would still have like c, depending on the different equation, you would have different c's still showing up here after your first two conditions. And so you may not be able to solve them for two variables directly. You may have to solve for the variables in terms of the other ones. But this time, it's a little bit easier. So we have c1 and c3 are both equal to 0. In general, you might have to say to solve this specifically for c1 and c3. And there we go. Either way, we should be able to assign that. And then if we return to v, we've got that it only involves c2 and c4. Okay, so that's a handy recap. Now the next equation, equation 3, simplify subs x equals L into v prime. And we need this to be equal to 0. So this one, again, we don't care about the beta. So maybe we can just divide that out. And now you have the option of either dividing by cosine or dividing by cos hyperbolic to solve for c2 or c4. And there's a hint in the question. Hint, you don't need to solve for this in order. Be careful not to divide by 0. And this is kind of necessary this case, because if we do divide by the cosine and solve for, let's say, c2 2 first in terms of C4 divided by this cosine, then we might get a 0 over 0 indeterminate form later, and that's not going to work itself out. So rather than that, what we're going to do is solve equation 3 for specifically C4. And now we're dividing by cos hyperbolic, which, unlike cosine, is never equal to 0 for any argument. So let's say that C4 is equal to this, and then we can recap what V is. Okay, so V now just involves C2, and we've run out of constants, coefficients in front to solve for. So now in this last step, what we're going to have to do is not solve for C, but get a generating function from this that tells us what beta needs to be. So simplify subs x equals L into V triple prime. Let's have a look. So here's the equation. And the equation 4 that we had after we sub in x equals L to V triple prime, maybe let's just have a look at V triple prime first. So here's V triple prime. If we substitute x equals L inside, then these cos hyperbolics cancel. Maybe it should be cosine rather than cos. Okay, that's like the long form of cos hyperbolic. All right, so and we're left with just the same thing twice. So we have this -2 cos of beta L times beta cubed. So we can get rid of this this beta stuff and the C2 in front. What we want to do to make this equal to 0 is have the cosine, the trig thing, take us to 0. So the generating function is just that cos of beta L is equal to 0. So after all of that work, we've arrived at our generating function. Maybe we can copy it in if you like. The generating function is cos beta L is equal to 0, which, unlike the cantilever one, which you can't actually solve for beta, this one is simple enough that you can say right away what the roots are. So this means beta L is equal to n plus a half times pi. So that's where cosine is going to be equal to 0, and this lets you solve for beta n. So beta n would be equal to n plus 1/2 pi all over L. Okay. So I guess we actually went ahead a little bit, because the question just asked us to figure out the mode shape expression, and so this is the general form of it, and after we substituted everything in, then we've got what our betas are, and the mode shape is the last thing just before this. So this is the mode shape expression. Maybe we could call that mode shape expression is equal to this, and the betas have a certain condition on them that we figured out right after that. So this is the mode shape expression. We solve for those betas and we can substitute them back in. So for any beta, this is it. For an artificial C2, and the generating function is cos of beta L is 0, which we can actually solve for beta n is n plus 1/2 pi by L. So now we're good to go. Determine the first 3 resonant frequencies. Well, we figured out earlier in this calculation that omega is, or that beta is this relationship between omega, mu, e, and I. And so we can go and change this around to figure out what omega is. So the first 3 resonant frequencies, and we don't know what EI over mu is, so this is going to be in general, right? So we've got the same expression here as for the cantilever. So this is going to be true for every single beam, and it's going to be that. So since beta n is this, the first three would be omega 1 would be, oh, maybe I'll do this in maple. Based on all of that stuff, we've got omega is equal to beta squared times square root of EI over mu. And beta is equal to n plus a half times pi by L. Okay, so there's the first, there's any resonant frequency. So we've actually got all of them in terms of a general expression. So n plus a half is going to be a half squared, and then 3 halves all squared, and then 5 halves all squared. Okay, and there we go. That's all the resonant frequencies. Plot the first 3 mode shapes on the same plot using maple. So we need to get an EI over mu. It's all going to be proportional to that, and then scale from 0 to L. So we can pick any L that we like. For this last part, they say EI over mu equals L equals 1. So let's give that a shot in the plot there too. So let's say that to make EI over mu equal to 1, let's take EI is equal to mu, and then let's take L is equal to 1. Then we've got omega, which is that, and we could figure out what beta is at each n. So we'll say V1 is equal to subs n equals 1 into V. That should sub in for the beta that we found. We can also get rid of this C2 thing. And we'll do the same thing for the next part. V2 will sub n is 2 into that, and V3 will sub n is 3 into that. And same thing for omega. Omega 1. Well, actually, I guess we just need to find the third one to compare with flex later. Omega 3 is equal to subs n equals 3 into V over C. No, into omega. Right. And let's put a new valve on that, just to make it a floating point. Okay, so we get omega 3 is 120, V3, oh, I guess we should simplify these because we want to get rid of that C2. So how about simplify that? That one and the next one. And what we should see is that we've got an expression which I guess still isn't super obvious looking, but when we plot this, we expect something that's going to look like resonant modes of a pin and roller support. So it should have no displacement at the left and no slope on the right. So the first mode maybe is like part of an air column kind of, and then it's going to go up and down over to that, and then up, down, up, or possibly inverted for all of these. So let's plot those. It's not the equations that we really want, it's the plots. V1, V2, V3 from x is 0 to L, and there we go. All right, so it looks like, oh, you know what we did? We substituted n equals 1 for the first mode, but actually we said that the first one would be at n is equal to 0. So maybe we can go all the way back and say, if we want this to be the nth mode and start it at 1, maybe we should really be saying n minus a half pi. We could just say that n starts at 0, but to make it still start at 1, we have to just redefine these things. No big deal. So that means this is one really nice thing about working with a computer algebra system. One change, and then we can rerun everything, and it'll recalculate perfectly. Okay, so the real third resonant mode, as opposed to the third overtone that we were figuring out before, the third one above the fundamental, this is really the third resonant mode. So this is 3 minus a half times pi. So this would be the 5/2 pi. Okay, that's this yellow one there. The green one is what we thought, and the red one is what we thought too. So beautiful picture of the modes, and we think the third one is going to be around 61.685. Okay, last one. Actually use Flex to model the beam and confirm the third mode shape and frequency for EI over mu is 1. Include a code and the code and a plot of the third shape with appropriate zoom. Okay, so the first thing to do is recap how Flex actually calculates these. Let's put the font back to something like 8 so you can see it a bit better. Right, so the syntax for doing this is the same stuff as we were dealing with before in Flex, except in this part, instead of saying that the net force is equal to 0, what you say is the net force is equal to the mass times acceleration. So this is really the force per unit volume, and so we've got mass per unit volume times the acceleration, which, if we're looking for a harmonic solution, would be negative omega squared times the actual displacement in x. So we say the x force is negative omega squared times mass per unit volume times the x displacement. Same thing in y, and same thing in z. All this is to do is to give it a little bit of a jolt so that it doesn't find the trivial solution. So we give it a little bit of a force, in this case the weight of the thing, to start it out moving, and then we can look for the actual resonant displacement after that. So then what we need to do in this particular setup, it looks like we've got a really old setup here where we have just the isotropic beam stuff set up in there. So we don't have any of the more advanced kind of single crystal stuff. What we can do is change around omega until we find a resonant frequency. So this is one that was done in class yesterday at time of recording, and we had already found the resonant frequency quite well. So when we zoom right in, you'll see something like this as you cross a resonance, that the actual displacement, in this case we're looking in y, goes lower and then flips as you cross a resonant peak, and then anywhere near the resonance you see the displacement in the beam would be somewhat close to the slope that you were expecting. So what we need to do is set up the boundary conditions to match the pin and the roller support for this for our particular setup. But before we can do that, we need to figure out what to put in for E, I, and mu. So the way to figure that out is, so rather not E, not I guess, but E, the dimensions, and then mu. So let's see. We have that EI is supposed to be equal to E times B times H cubed over 12, where H is the thickness, B is the width, and E is the stiffness. So if we want EI over mu to be equal to 1, then we can just we have a lot of options here. We can really just pick a size for EI for B and H. Let's just say that B is equal to 0.2, H is equal to 0.1, and L is equal to 1. Then what we're going to do is say that E is equal to 100E9 to make it a little bit more typical, and we can figure out what our mass per unit length needs to be. And then from the mass per unit length, we can figure out what the density has to be. Rho is supposed to be equal to mu divided by the cross-sectional area, which is h times b. Yeah, is that right? Yeah, that's it. Because you would take the mass per unit volume and then multiply by the cross-sectional area to get mu, or really integrate over the cross-sectional area if the density is changing with position. Okay, so this is saying that the density is actually pretty massive in this particular case from the setup that we've got. So to get EI over mu to be equal to 1 for this case, we need a totally unrealistic density of 8.3 E7 or 0.83 E8 or 83 million kilograms per cubic meter, which is I don't know, some sort of like partially collapsed neutron type thing. So that's kind of cool. All right, so we said this is the thickness. This is going to be the, or rather, this one's the width in Z. Let's make this the thickness in Y. 1. We've got 109, I think, and then we're going to need 83 E6 for the density. And we're looking for resonant frequencies that are probably around 60. So let's just start off with omega is equal to 10 times stage. So we'll look between 0 and 100 and just see what we've got in this setup. We're also going to need to set up the boundary conditions. And maybe to start things off, since the density is so huge, let's pretend we're not on Earth. We'll go 9.81 over 1e5 just to make it a much smaller perturbation in y so that doesn't mess things up. Okay, so at the x equals Lx surface, we need that it is free in y, but it can't actually angle, so that's fixed in x. The value in z just tells you whether it can move back and forth in z. Let's say that that's 0. And on the x equals 0 surface, we're going to say that it's fixed in y, can't move up and down, but it can angle. So that means the x parts have to move in and out. Again, we're not going to let the z move. So to try to shut down everything in the width direction a little bit, this is going to make it a little bit stiffer than it would be if it was totally free in z. So we could expect that the resonant frequencies will be a little bit higher in flex from that boundary condition. Okay, let's see what we get. So between 5 and 6, there's some action going on. We've got some bigger thing near the fundamental, and you can see the mode shapes that we're looking at here. We've moved up towards a much higher resonance than we were thinking. If we plot this again and then keep an eye on this as we're going, that's towards the fundamental. That's like the secondary mode. That one is looking like the third mode there, right around between 5 and 6 as expected. Okay, so let's go and zoom in the frequency. So let's say 50 plus 1 times stage, and see what we get. Looks like we're approaching a resonant mode there. Oh, that's pretty close. Ooh, this is a tricky situation. It looks like it's, because this one is just slightly above 0 over here compared to this, that tells you that it is very close to stage 7, but slightly towards stage 8. So if we go back here, we expect that it's going to be pretty close to 57, but a very small amount above it, probably less than 0.1. So maybe let's go with 56.9 plus 0.1 times stage. Yeah. So that was between the first stage and the second stage. And that tells you that we're between adding 1 and 2 to that. So that's 57 plus 0.01 times stage that we can zoom in on. Have we crossed it already? Yep, it's in the first, we've just caught it there. It's in the very first one, so it's after stage 1. So 57.01 plus 0.001 times the stage. Okay, now you see we're getting close enough to the resonant frequency that you can actually see the beam deforming even at this magnification. The mode shape has been visible over here for a while. So we've got something extremely close to 57. Again, between stage 1 and 2. So let's just look at the beginning of that again, where you can see the thing deforming. You'll see even more at the next one when we go between 57.011, and then we'll add another decimal on the frequency that we're looking for here. So this is getting closer and closer to the resonant frequency, and then it's going to switch right as it crosses. The deformation is getting so big that the magnification is exaggerating it to the point where it doesn't look realistic anymore. But this is a good spot to stop here. So you could take a picture of that. You could go and copy it in, and you've got a beautiful setup for what the mode shape looks like. Plot of the deformation with position, and this is at a frequency which is basically there. Specifically in this plot, it looked like we were at between 7 and 8, so that gives us another decimal point on the frequency. So basically that. Looks a little bit closer to 7, so we'll go with that. Okay, so how did things compare between Maple and Flex? It looks like the calculation we got with Maple was off by a bit. It got, we'd calculated a higher resonant frequency in Maple than we had calculated in Flex this time. The Flex calculated frequency was a little bit lower, but not by a lot. To recap what we did today, we looked at the full dynamic beam equation and said where it comes from, and then how you go from there to the reduced beam equation by assuming a harmonic solution in for your v at xt to find an expression for just v hat at x. Then it compared to the cantilever solution and looked at how you can apply arbitrary boundary conditions at each end of this beam. So say pin supported and roller supported to solve for a new mode shape expression for that particular set of boundary conditions and a generating function, what that means, and then how to use that to get the resonant frequencies and plot the mode shapes in Maple, then compare with the solution method in Flex PDE. This is the last of the video series for 2P for 2018, and the course is really revamping for 2019. So I hope that you've really enjoyed this and get the most use out of this as possible. It's been a lot of fun. See you in class.